Since discriminant analysis is a classical statistics technique and a model-driven method, performing discriminant analysis correctly requires the satisfaction of two important assumptions. The first assumption is that predictor measurements in all classes should come from a multivariate normal distribution. When this assumption is met, discriminant analysis tends to outperform other classification methods such as logistic regression. However, in practice, discriminant analysis performs well even the predictors have non-normal distribution or are dummy variables that have the values of either ones or zeros if the dataset is sufficiently large. In most analytic situations, we tend to have relatively large datasets, so this assumption may not be problematic. However, discriminant analysis is sensitive to outliers, so prior to performing discriminant analysis, it is recommended that outliers be removed from the dataset. The second assumption is that the correlation structure between the different predictors within a class is the same across classes. Whether your data meets this assumption or not can be easily checked by inspecting the correlation matrices between the predictors for each class. If the correlation matrices are roughly the same, then this assumption is considered met. If the correlation matrices are very different, then discriminant analysis tends to classify records into the class with the largest variability. So the analyst needs to be aware of this potential issue. One solution to the violation of this assumption is to use quadratic discriminant analysis instead of linear discriminant analysis. Quadratic discriminant analysis is a less popular type of discriminant analysis that allows for non-linear separation of data. We won't discuss quadratic discriminant analysis in this course, but you can find more information about this technique online and how it is implemented in software products if you are interested. Finally, let's discuss some of the practical considerations when performing discriminant analysis. First, let's talk about how to deal with prior probabilities. Discriminant analysis assumes that in a binary class situation, the chance of encountering a record from either class is the same. For example, in our case, the method would assume that the chance of a bank customer responding to the home equity line of credit is 0.5, and the same chance for not responding to the offer. Suppose that, from experience, the bank manager knows that only 15% of the bank customers would respond to a home equity line of credit offer, and the rest 85% would not. There is a simple way to adjust the classification function to account for the prior probabilities. Let's say that Pj is the prior probability of membership in class J. So in a binary class situation, the probability of the case belonging to class J is Pj, and the probability of the case belonging to the other class is 1 minus Pj. We would simply add the natural log of Pj to the constant of the classification function for class J, and the natural log of 1 minus Pj to the constant of the classification function for the other class. For example, in our Sunnyvale Bank example, the constants in the original classification functions are negative 6.25 and negative 1.2, respectively. To account for the prior probability of 0.85 and 0.15 for class 0 and class 1 respectively, we simply add the natural log of 0.85 to the constant of class 0 classification function, which is negative 6.25, and add the natural log of 0.15 to the constant of class 1 classification function, which is negative 0.12. And we are going to get negative 6.41 and negative 2.02 for the constants for class 0 and class 1 respectively. Now let's think about what happens here. Because of the fact that log of 0.5 is larger than the log of 0.15, this adjustment resulted in a bigger difference between the constants for the two classes. As a result, the classification score for class 0 will more likely to be larger, resulting in a higher chance of cases being classified into class 0. Of course, the same effect can be achieved by simply adjusting the cutoff probability value once the classification scores have been converted into probabilities. The second practical consideration is relevant to unequal misclassification costs. In real-life situations, misclassifying cases into one class or another class tends to have different misclassification costs. For example, in our case of home equity line of credit offers, misclassifying a customer who does not respond into the response class would mean wasting the cost of mailing of a promotion offer or making a phone call. But misclassifying a customer who would respond into the non-response class would mean losing the revenue from the business opportunity, which is much more than the cost of a mailing or a phone call. So how would we account for the unequal misclassification costs into our classification functions here? A similar approach as the method we used to deal with prior probabilities can be employed here. We can adjust the constants in the classification functions to help classify more cases into one class than the other class. In this case, instead of adding the log of prior probabilities to the constants, we will add the log of misclassification costs to the constants. For example, let's denote the misclassification costs of misclassifying a class 0 case as a class 1 case as C0, and the misclassification costs of misclassifying a class 1 case as a class 0 case as C1. We will simply add the natural logs of C0 and C1 to the constants of the classification functions for class 0 and class 1 respectively. Whichever class has the higher misclassification cost would result in higher classification scores, making it more likely to classify cases into that class. For example, if misclassifying a class 1 case as a class 0 case is much more costly. Then the classification function will be adjusted to make it more likely to classify cases into class 1, resulting in less misclassification for class 1 cases. In many situations, it is very difficult to estimate the misclassification costs accurately. But it may be easier to estimate the ratio of the misclassification costs between classes. For example, we may say that misclassifying a class 1 case as a class 0 case would cost 10 times as much as the other way around. Or, in other words, C1 divided by C0 equals to 10. With that information, we can also make the appropriate adjustment to the constants. Without knowing the actual misclassification costs, we can assume that C0 is 1 and C1 is the misclassification cost ratio, and in this case it happens to be 10. Since the log of 1 is 0, no adjustment is needed for the constant of the classification function for class 0. For the classification function for class 1, you simply need to add the natural log of the misclassification cost ratio, which is C1 divided by C0, or 10 in our case, to its constant. This adjustment again results in classifying more cases as class 1 cases to avoid high misclassification costs. As you can see, this effect can also be achieved through adjusting the cutoff probability value once the classification scores have been converted into probabilities. But the tricky part will be knowing how much the cutoff probability value needs to be adjusted if you do that. So these are some of the recommended adjustments you can make when it comes to performing discriminant analysis when there is prior probabilities and unequal classification costs. Now that we understand how discriminant analysis works, let's look at two examples and solve them using data mining software packages. The first example is an expanded version of the Sunnyvale Bank customer case we have been using throughout this lecture. Hayden from Sunnyvale Bank has compiled data on 500 customers who received home equity line of credit offers from the bank in the past, including their age, sex, income, and whether they responded to the offer or not. And Hayden wants to use the dataset to develop a discriminant analysis model to predict whether a customer would respond to a home equity line of credit offer or not, and use the model to score the 20 new customers in the score dataset. Since one of the key advantages of discriminant analysis over logistic regression is that it can deal with more than two classes, we are going to look at a problem that deals with more than two classes here. The concepts are still the same. For cases where there are more than two classes, one classification function is generated for each class. So for a 3-class problem, there will be 3 classification functions. The class with the highest classification score is the predicted class, and the classification scores can be translated into probabilities just as in the 2-class cases. In our example, we are going to look at traffic accidents that resulted in no injury, non-fatal injuries, and fatality, and try to predict the severity of the accidents based on predictor variables such as weather, day of the week, road condition and type, and etc. This prediction would be extremely useful to 911 dispatchers that need to make decisions about which units to send to the scene of the accident to make the most effective use of the limited resources. We will look at how discriminant analysis can be used to make classifications in this three-class situation.